Welcome to AskPrep, your trusted companion for NEET and JEE preparation. Today we will study about a very important topic of chemistry, which is electrochemistry, Nernst equation and electrochemical cells. This is a crucial topic for both NEET and JEE aspirants, and understanding it thoroughly can help you solve numerical and conceptual questions with ease. So, let's dive right in. To begin with, let's take a moment to understand what electrochemical cells are and how they work. An electrochemical cell is a device that converts chemical energy into electrical energy or vice versa through a redox reaction. A typical electrochemical cell consists of two electrodes, which are immersed in electrolyte solutions, and these electrodes are connected externally by a wire through which electrons flow. The two half cells of the electrochemical cell are where the oxidation and reduction reactions occur. In the electrochemical cell, the electrode where oxidation takes place is known as the anode, and the electrode where reduction occurs is called the cathode. Since electrons are released at the anode and travel through the external circuit to reach the cathode, the anode is considered the negative terminal, and the cathode is the positive terminal. The flow of electrons from the anode to the cathode generates an electric current that can be harnessed to perform useful work. A classic example of an electrochemical cell is the Daniell cell, where zinc and copper electrodes are placed in their respective sulfate solutions. Zinc undergoes oxidation by losing electrons, while copper ions gain these electrons at the cathode, resulting in the deposition of copper metal. The difference in potential between the two electrodes drives the flow of electrons, and this potential difference is known as the cell potential or electromotive force, EMF. But here's where it gets interesting. The cell potential under standard conditions can be calculated easily, but real-life conditions are rarely ideal. The concentration of ions in the electrolyte solution can vary, and these changes affect the overall cell potential. This is where the Nernst equation comes into play, allowing us to determine the cell potential under non-standard conditions. Now, let's talk about how the Nernst equation helps us modify the cell potential based on changes in concentration, pressure, or temperature. It accounts for these variations by incorporating the reaction quotient, which reflects the ratio of the concentrations of the products to the reactants at any given point. The Nernst equation adjusts the standard cell potential to reflect real-time conditions, giving us a more accurate value of the cell's potential. The beauty of the Nernst equation lies in its ability to predict how the cell potential will change as the concentration of ions changes. If the concentration of reactants increases, the reaction tends to shift forward, and the cell potential increases. On the other hand, if the concentration of products increases, the reaction shifts backward, leading to a decrease in the cell potential. This dynamic behavior of electrochemical cells is governed by the principles of chemical equilibrium, which ties electrochemistry closely with thermodynamics. The Nernst equation also explains an interesting phenomenon known as concentration cells. In a concentration cell, the electrodes are made of the same material, but the electrolyte solutions have different concentrations. The difference in concentration between the two half cells generates a potential difference, which drives the movement of electrons. As the concentrations become equal over time, the cell potential approaches zero, indicating that the system has reached equilibrium. A practical application of the Nernst equation can be seen in pH measurement using a glass electrode. A pH meter essentially functions as a concentration cell where the voltage generated between the reference electrode and the glass electrode is used to calculate the hydrogen ion concentration, thereby determining the pH of the solution. Another significant application is in batteries and fuel cells. Modern lithium-ion batteries, which power everything from smartphones to electric vehicles, operate on the principles of electrochemical cells, and their efficiency and performance are closely tied to the principles governed by the Nernst equation. Similarly, fuel cells, which convert chemical energy from hydrogen and oxygen into electricity, also rely on electrochemical principles. Let's now explore a real-life scenario where the Nernst equation plays a critical role: corrosion. Corrosion, particularly the rusting of iron, is an electrochemical process where iron acts as the anode and undergoes oxidation, while oxygen is reduced at the cathode. The Nernst equation helps predict the rate of corrosion by considering the concentrations of ions involved in the reaction. This understanding allows us to take preventive measures, such as galvanization and the use of sacrificial anodes, to protect metals from corroding. The concept of electrochemical cells and the Nernst equation also helps us understand electrolysis, a process where electrical energy is used to drive a non-spontaneous reaction. In electrolysis, an external voltage is applied to force electrons to move in the opposite direction, reversing the natural flow of the electrochemical cell. This process is widely used in industries for applications such as metal extraction, electroplating, and the production of chemicals like chlorine and hydrogen. The Nernst equation also provides insights into the concept of equilibrium in electrochemical cells. When a cell reaches equilibrium, the cell potential drops to zero, meaning that no net reaction occurs. This is the point where the forward and reverse reactions happen at the same rate, and the system achieves a stable state. Understanding this concept helps us predict the behavior of electrochemical cells and their efficiency over time. In competitive exams like NEET and JEE, you can expect both conceptual and numerical questions related to the Nernst equation and electrochemical cells. You may be asked to calculate the cell potential under non-standard conditions, predict the direction of the reaction, or analyze the behavior of a concentration cell. Mastering these concepts will not only help you score well but also build a solid foundation in electrochemistry, which is essential for higher-level studies. Thank you. We hope this video has helped you gain a clearer understanding of hydrogen and its compounds, especially the fascinating role of heavy water and isotopes. If you found this video helpful, make sure to like, share, and subscribe to AskPrep for more in-depth chemistry lessons. Keep studying, stay curious, and good luck with your exams.